Now that we have studied solutions, let's understand how we talk about their systems in terms of concentrations. Concentration is the relationship between the amount of solute and a specific amount of solution in which it is contained. There are many units that can be utilized for concentrations, but for us in this course, we're going to focus on molarity. Molarity is basically the relationship between the moles of solute and the liters of the solution. To present to you other units of concentration, here we have mass percent. In mass percent, it is actually defined as the grams of solute divided by the addition of the grams of solute and grams of solvent. This term can also be known as the grams of solution times 100%. Then we have volume percent. In volume percent, we have the milliliters of solute divided by the milliliters of solution times 100%. And lastly, we have mass per volume percent, which is the grams of solute divided by the milliliters of solution times 100%. So even though mass percent, volume percent, and mass per volume percent are also units of concentrations, you are not responsible for using them in mathematical problems. We are only going to focus on molarity. So with that, let's actually understand how to specifically calculate or express molarity for different solutions. First, let's understand that molarity equals moles over liters of solution. And remember that these moles are going to be moles of solute. In the practice problem that we have on letter A, we need to express the concentration of the following solutions in terms of molarity. On letter A, it actually says 2.00 liters of solution contain 1.50 moles of solute. So for letter A, I'm giving the moles of solute, so I express it as molarity equals 0. Let me fix this. 1.50 moles of solute divided by 2.00 liters of solution. So when I divide 1.50 divided by 2, my result is 0.750. And the unit for molarity is a capital M, which is known as molar. Let's do the second problem. In the second problem, I'm given 10.3 grams of isopropyl alcohol. And then we have a solution that is 315 milliliters. So my solute was given in grams, 10.3 grams. The chemical formula for isopropyl alcohol is going to be C3H8O. The molecular weight of isopropyl alcohol, when I take the mass of carbon specifically, I'm going to do 12.011 times 3 added to 1.008 times 8 And we are going to add 15.999 for oxygen. So the molecular weight for isopropyl alcohol is 60.096 grams per mole. The reason why I'm calculating that is because I need a molar amount for my solute, and right now it's given in grams. So if I take 10.3 and I divide it by 16.096 grams in 1 mole, then I can change my solute into moles. 10.3 divided by 60.096. That means that this is going to be 0.171 moles of our solute, which is isopropyl alcohol. Next, since my volume is 315 milliliters, I need to change it to liters. So I'm going to say 1,000 milliliters over 1 liter means that this is 0.315 liters. And now I can calculate molarity. The moles of solute is 0.171 moles. The liters of solution is 0.315 liters. So if I do 0.171 divided by 0.315, I find a molarity that it is 0.543 molar. Another important calculation that we need to be familiar with when it comes to solution is the formation of diluted solutions. In a solution preparation, we can actually make a less concentrated solution by diluting a concentrated solution with a solvent, which is usually water. When it comes to this, we can utilize a mathematical equation to calculate what is needed to make this diluted solution. The equation utilized, you can see it here on the slide, which is equation 6.12, which in this equation, we're going to have initial molarity times initial volume equals final molarity times final volume. Notice that on the left side of the equation, we have the molarity and volume for the concentrated solution. And on the right side of the equation, we have the diluted molarity and volume. Let's actually do a practice problems to understand how to use this equation in order to calculate what it needs to be used in order to create a diluted solution. So let's say that we need to prepare a 250 milliliters of a 0.100 molar sodium chloride solution utilizing a 2.00 molar NaCl solution as a source of NaCl. One of the important things when it comes to utilizing the dilution equation is that we do not change volume into liters. You need to just make sure that the units of volume are the same, but it is not a must to convert milliliters to liters. So when it comes to this equation, I can identify that this is going to be the volume that it gets prepared. So this is going to be V2. We need to make this concentration of the solution. So this is M2. And this last term is going to be the concentrated molarity. So that's M1. So in this problem, we are solving for V1. Utilizing this equation and doing some algebra, I can actually separate the V1 term by itself. So V1 equals M2 times V2, everything divided by M1. Then I'm going to plug in all of my numbers. M2 is 0.100 molar multiplied by V2, which is 250 milliliters. Everything is divided by 2.00 molar. The molar unit cancels. That means that my result is going to be in milliliters. So when I take 0.1 times 250 divided by 2, that means that if I round this specifically to 2 sig figs, because 250 milliliters is 2 sig figs, this is going to be 13 milliliters. Earlier in this chapter, we actually explored how different types of mixtures, including solutions, colloids, and suspensions, can be separated or not with different physical methods. And I mentioned that this had to do specifically with the concepts of osmosis, and later we're going to see also how this is related to dialysis. Let's first discuss what is osmosis. Osmosis is going to be the process in which solvent molecules flow through a semi-permeable membrane into a solution. This semi-permeable membrane is a biological or synthetic membrane that will allow only certain molecules to pass through via diffusion. And in the case of the solids that we have already explored, we actually observed that a semi-permeable membrane, like the little sac that we saw in the different physical methods for filtration, will only allow the substances, specifically in a true solution, so meaning a homogeneous mixture, pass through the membrane. Understand that when we have a semi-permeable membrane in place, osmosis is going to specifically allow some of the solvent particles to move. In this system, understand that osmotic pressure plays a role. And osmotic pressure is the hydrostatic pressure required to prevent a net flow of solvent through the semi-permeable membrane into a solution. In the image that we have on the left side of the slide in figure 6.31, we see an illustration for osmosis. What we observe overall is the presence of the semi-permeable membrane, and we see that specifically in the container, we have a sugar solution and we have pure water. Overall, what we observe here is that this semi-permeable membrane is going to be separating my sugar solution from pure water. And over time, at least in this example, we can observe how the volume increase in the second compartment where we had the sugar solution, because this semi-permeable membrane allowed water molecules to move from one compartment to the next. One of the interesting things is that this movement of substances happens in cells. And tonicity is specifically the term that refers to the relative concentrations of solutes in a solution compared to inside of a cell. So since our cells can actually have this flow of solutes in solutions move from inside to the next, one of the things is that tonicity is going to determine the direction of water movement across the cell membrane via osmosis. Tonicity is going to change how much water enters or leaves the cell, and understand that this is going to have repercussions in terms of the size of the cell. Lastly, tonicity is going to influence specifically three types of different solutions, which are known as hypertonic, isotonic, or hypotonic. So let's see how hypertonic, isotonic, or hypotonic solutions are going to be affecting the cell. Specifically, here we have the illustration of how it is affecting red blood cells. When it comes to applications, let me just state that this whole idea of hypertonic, isotonic, and hypotonic solutions in your future professions is reflected pretty much in how IV fluids are given to a patient. Let's first look at a hypertonic solution. A hypertonic solution is going to be a solution where there is higher solute concentration outside of the cell compared to inside of the cell. When you put a cell in a hypertonic solution, because cells want to be equilibrated and they want to manage what happens to overall the substances inside and out, and they try to, in a way, equilibrate. One of the things that we see is that in a hypertonic solution, when a cell is placed in it, water is going to exit the cell. And upon water exiting the cell, because now in the hypertonic solution, we have a higher solute, the cells are going to tend to shrink, or in other words, they're going to undergo crenation. And we can see how that looks like in the first illustration. If cells are put in an isotonic solution, there is the same amount of solute concentration outside of the cell and inside of the cell. So when you have an isotonic solution, since water moves equally in and out of the cell, we see that the cell itself is going to have no change in its size, as we can see in the middle illustration. Lastly, if a cell is actually placed in a hypotonic solution, this means that the solution is going to have a lower solute concentration outside of the cell compared to inside of the cell. So the effects of hypotonic solutions in cells is that water is going to enter the cell, it's going to swell it, and possibly it can rupture the cell. And that is known as hemolysis, which means that because of the swelling, the lysis means breakage of the red blood cell. The last concept that we need to explore in this chapter is dialysis. Dialysis is a medical procedure that removes waste, excess ions, and fluids from bloods when the kidneys no longer perform this function. As you can see in the illustration on the left side of the slide, here we have a patient that when they are undergoing dialysis, blood is drawn from the patient and filtered through a dialyzer. A dialyzer, which the image here is just enlarging what it looks like, is what is known as an artificial kidney. And what happens is when the blood is removed from the patient, and then pass through the dialyzer. Then inside of the dialyzer, as we can observe, there's going to be a semi-permeable membrane that separates the blood from the cleansing solution. And overall, since the kidneys in the body cannot filter out those excess ions or waste, when the blood is passed through the artificial kidney, the waste materials and excess ions are going to pass through the semi-permeable membrane into the cleansing solution, and that's how the blood gets cleaned, and clean blood is then returned to the patient in the process.